The device you are holding right now started as a rock, not a rare mineral, but quartz sand, the most common substance on Earth. Yet, we turned this sand into a brain that performs billions of calculations every second. Look at a modern smartphone. Its heart is a microchip, and silicon makes up the majority of this chip. Silicon is the second most abundant element in the Earth's crust, right behind oxygen. However, you cannot simply dig up sand and build a computer. Natural silicon is locked inside chemical compounds, bound tightly to oxygen as silicon dioxide. Breaking that bond is the first major obstacle. The process begins at a metallurgical smelter, where workers dump quartzite gravel into massive electric arc furnaces. They add carbon sources like coal and wood chips, heating the mixture to over 1700 degrees Celsius. At this temperature, the carbon pulls the oxygen away from the silicon, leaving behind liquid metallurgical-grade silicon. This molten substance is 98% pure. While sufficient for steelmaking, this grade is useless for electronics. If you build a microchip from it, impurities will cause the electrical signals to wander, collide, and fail completely. To make chips, silicon must be refined to a level of purity that defies imagination. We need electronic-grade silicon, where only 1 in a billion atoms can be an impurity. To reach this 9/9 purity, engineers convert metallurgical silicon into trichlorosilane gas. Distilling this gas repeatedly separates the pure silicon from contaminants, which is then deposited onto heated filaments inside a reactor. This chemical vapor deposition creates high-purity polycrystalline silicon. To push purity further, a float zone process passes a heating coil along a silicon rod. Impurities gather in the moving molten zone and are swept to the edge, leaving the rod incredibly pure. But even 9/9 silicon is still polycrystalline, meaning its atoms form a chaotic jumble of misaligned grains. Electrical signals scatter at these grain boundaries, so a chip requires a single, continuous crystal lattice. To build this, manufacturers use the Czochralski process. They melt the silicon in a quartz crucible at over 1400 degrees Celsius, then lower a tiny seed crystal of pure silicon into the melt. As the seed slowly rotates and pulls upward, molten atoms align perfectly with its structure. The cooling silicon forms a cylinder called a boule. Weighing over 100 kilograms, this boule is a single, flawless crystal with atoms aligned in a perfect geometric grid. Next, a precision wire saw cuts the boule into paper-thin wafers less than a millimeter thick. Slicing damages the silicon surface, leaving microscopic scratches. To correct this, machines grind and polish the wafers using chemical-mechanical planarization. This step removes material at the molecular level, creating a mirror finish. The wafer becomes the flattest surface ever created. If a wafer were scaled to the size of the Earth, the tallest bump on its surface would be only a few inches high. The polished wafer is now ready for photolithography, which prints the circuit design onto the silicon. Because the circuits are far too small for mechanical tools, engineers use light. They coat the wafer with a light-sensitive polymer called photoresist, then project extreme ultraviolet light through a mask containing the circuit pattern. This light has a wavelength of just 13.5 nanometers, which alters the exposed photoresist. This incredibly short wavelength allows engineers to print features smaller than a human virus. The precision required is staggering, as a single speck of dust can ruin the entire wafer. Because of this, lithography takes place in cleanrooms millions of times cleaner than an operating room. Workers wear protective suits, and robotic arms handle the wafers. Inside the machine, complex, multi-layered mirrors focus the ultraviolet light to shrink the circuit pattern. These mirrors must be polished to a precision of a fraction of a nanometer. The machine steps across the wafer, printing patterns onto hundreds of individual chips. If the pattern shifts by even a few atoms, the layers fail to align and the chip is ruined, scrapping the entire wafer. After exposure, a chemical developer washes away the softened photoresist, leaving a protective polymer template. The wafer then enters an etching chamber, where reactive gas eats away unprotected silicon to carve deep channels. Once the photoresist is stripped, a raised pattern of three-dimensional silicon remains. But pure silicon is a semiconductor and does not conduct electricity well on its own. To control current, engineers modify its conductivity through ion implantation, or doping. Firing high-energy beams of impurity atoms into the silicon, they use phosphorus to create negative N-type regions with extra electrons, and boron to create positive P-type regions. By pairing these N-type and P-type regions, engineers build transistors, the basic electronic switches of computing. A transistor features a source, a drain, and a gate. Applying a tiny voltage to the gate creates a channel that lets electricity flow between source and drain, while removing it stops the current. This simple on-off state represents the binary ones and zeros of digital data. A finished microprocessor requires repeating the lithography, etching, and doping steps dozens of times to build up to 80 layers of circuitry. Between these layers, engineers deposit microscopic copper wires. A single chip, smaller than a fingernail, can contain over 100 billion transistors. The entire fabrication process takes up to 3 months. It requires hundreds of individual steps, billions of dollars of equipment, and the most complex supply chains on Earth. A single wafer moves through thousands of machines, traveling across the cleanroom in automated pods. The complexity is staggering, yet it all starts with quartz sand heated in a furnace. Humanity has learned to take the most common substance on the planet and organize its atoms with atomic precision. We turned a handful of beach sand into a machine that can think. Next time you hold your phone, remember, you're holding 3 months of work, starting from a rock.